Yeah. So let's start. I have started the recording, and please just unmute yourself and talk to me if you have any doubt, because last week we were having this problem of audio problem. Now I think it's gone now. Okay. So yeah. Good evening to all the students. I am Sai Krishna, one of the TA for your electrical machines course. And yeah, this week we have discussed about like in the transformer, different kinds of tests. What are the equivalent circuits of the transformer? What is the equivalent circuit of the transformer referred to primary side? What is the equivalent circuit of transformer referred to secondary? And what kind of equivalent circuit parameters will be there? What are the different kinds of parameters in an equivalent circuit? And how we can find the equivalent circuit by conducting some simple tests, that is short circuit tests and open circuit test, and yeah, and more concepts other than this we have discussed this week. Now, in today's session, we will be looking after some concepts related to equivalent circuit of a transformer and also tests in this transformer, that is open circuit test and short circuit test. So yeah, let's look into it. Someone has joined. Let me just let them just in. Yeah. So now I hope you all can see the first question on the screen. So yeah, we were given a transformer. We were given the ratings of the transformer, that is 100 kVA, 2200/440 volts. That is high voltage side is 2200 volts and low voltage side is 440. When we conducted two different tests on a transformer, open circuit as well as short circuit, the test results are here. Test results are nothing but the readings of the instruments inside the circuit. So whenever we are connecting a test, whether it is short circuit or open circuit, we are connecting a voltmeter, an ammeter and a wattmeter, and we will proceed with the testing, whether it is open circuit or short circuit. Once we complete the test, and we will note down the readings, and those are given here. So test is already done. We were having the readings of all the voltmeter, ammeter and wattmeters in both tests. Now we were asked to find all the equivalent circuit parameters. One second. So we are asked to find all the equivalent circuit parameters within the transformer. Yeah. Now, before going into solving this question, let's see what are the equivalent circuit of the transformer. So how does an equivalent circuit of a transformer looks like, and what are these two tests? What is open circuit test? What is short circuit test? So which parameters we can calculate individually from OC, open circuit test, and which parameters we can calculate from the short circuit test. So let's take a separate sheet. Let's work out in this sheet itself. Yeah. Let me place my video here. Yeah. So before going into solving the actual question, let's discuss some concepts on the equivalent circuit of transformer, as well as what are the tests that are performed on the transformer, so that it will be very easy to solve for the problem, today's problem. Yeah. So let me just draw the equivalent circuit of transformer referred to primary, and then I will draw the equivalent circuit of transformer referred to secondary, and we will see what parameters are there, what are the equivalent circuit parameters. Then we will see how we can find this. So if you also remember the equivalent circuit of the transformer from the lectures you have heard this week, please try to draw along with me the equivalent circuit of the transformer, and we will see how we can proceed then. circuit of transformer referred to primary side. Yeah. So usually I'm just drawing here primary, secondary. Let's say this is a transformer, and now I'm trying to draw the equivalent circuit here. In the primary side, we know we have a core loss component and magnetizing current component, as well as the primary resistance and impedance. On the secondary side, that is load side, we will have the resistance and impedance of the load side, that is secondary. So I'm just combining everything and drawing it in here. You will see. Core loss, this is the core loss resistance, and this is magnetizing reactance, and this is the parallel branch that is responsible for the core loss. We are modeling the core loss and magnetizing branch inside a transformer within this branch, that is a parallel branch here. And so this resistance is the combination of both primary and secondary resistances. That is, let's say we denote this by RE1 and XE1, and yeah, now there is some current I1, and this particular current is I2 dash, this is I0. Yeah, now the current flowing here in this branch, that is through the core loss resistance RCL, will be ICL1, and the current flowing through the magnetizing reactance will be IM1, and this current we already named it, that is I2 dash. Now let's write what are the individual values. Now we see here RE1 is equals to R1, that is primary side, and R2 dash. R2 dash means the secondary resistance referred to primary, because we are drawing the entire equivalent circuit referred to the primary side. Okay. Now let's say the turns ratio is A. Now R1 plus R2 dash, R1 plus R2 dash, R2 into A square. So since the last 2 weeks we have discussed this. So if we know the turns ratio, we can just refer to any parameter to any side. Since we are referring our secondary resistance to primary, we have to multiply with the square of the turns ratio. Now XE1, what is XE1? X1 plus same thing, primary reactance plus secondary reactance referred to primary. Now X1 plus X2 into A square. Yeah. Now we will have a voltage here, V2 dash, and let's say supply voltage V1, V2 dash, A times V2, I2 dash, this current. How much is I2 dash? Secondary current divided by I, A, that is the turns ratio. Yeah. So V1 is equals to the total voltage, supply voltage will be V2 dash, that is the secondary output terminal voltage, plus the drop I2 dash into RE1 plus J XE1. Yeah, so this is the equivalent circuit of the transformer referred to primary. So we have referred the secondary resistances R2 and X2 to the primary. On the primary side, we are already having the core loss branch and its own primary and primary resistances and impedances, that is R1 and X1. So this is the equivalent circuit of transformer referred to the primary. Now let's see the same referred to secondary. Equivalent circuit secondary side. Yeah. Now in the secondary side it has R2 and X2. In the primary side we have core loss resistance RCL, magnetizing reactance XM, and primary resistances and reactances R1 and X1. We have to refer all these four equivalent circuit parameters to the secondary side. We will see how we can do that. One second, someone has joined. Yeah. Now since we are referring the first primary to the secondary side, we will give the names core loss 2 and this one is JXM2, and this side we have resistances RE2 then XE2. Yeah, so the current flowing will be I2 and the supply current will be V1 dash and the output voltage will be V2. Yeah, this current will be I0 dash. The current flowing to RCL2, ICL2, this will be IM2. Yeah, the current will be I1 dash. So this is more or less the equivalent circuit referred to secondary. Now we will write the same thing, individual values of the each equivalent circuit parameter. Now RE2 is equals to R1 dash. The dash will be for R1 because the primary we are referring to secondary, and R2 will be as it is. And since the turns ratio is A, R1 by A square plus R2. Now this is XE2, X1 dash plus X2, where X1 by A square plus X2. And what else? We have the core loss component here, RCL2, that is nothing but RCL1 primary referred to the secondary. And what else we have? XM2 we have. XM2 is nothing but XM1 referred to this one. Yeah, and here we also have the current I0 dash. I0 dash is I0 multiplied by the turns ratio, because that is all again referred to the secondary side. Okay, now with these two equivalent circuits, we know how many equivalent circuit parameters are there, unknowns, that is RE2, XE2, RCL, that is core loss resistance, XM, magnetizing reactance. So these are the 4 equivalent circuit parameters which we have to calculate. Now let's say someone have given to you a transformer and asked you to find the equivalent circuit parameters. These are all approximate equivalent circuits. Now from this equivalent circuits and with an actual transformer, let's say someone asked you to find these equivalent circuit parameters, all the equivalent circuit parameters of a transformer. How will you proceed? To determine the equivalent circuit parameters, we have 2 different tests, that is open circuit test and short circuit test. Now we will see which test will give us which parameters and why. So everyone now has an idea of the equivalent circuits, 2 different equivalent circuits having 4 equivalent circuit parameters. Now let's see how to determine those equivalent circuit parameters with a simple open circuit and short circuit test. First, let's see the open circuit test. It's a short for OC, open circuit. And 1 second, someone has joined. Yeah. Open circuit, and there is another name for it, that is no load test. Yeah. This test, we say it is usually conducted on LV side. So what's the reason behind that? We will get to that at the end of the discussion for this test. But let me tell you, the condition is we usually conduct this open circuit test on the LV side, that is low voltage side, by open circuiting the high voltage. So there will be a low voltage coil and high voltage coil for a transformer. Once you are provided with the transformer, you know what is the ratings of the transformer. And once you know the ratings of the transformer, you can able to say which one is low voltage, which one is high voltage. And to conduct this open circuit test, take the transformer and open circuit the high voltage side and conduct the test on the low voltage side. So to be more clear, let me draw the setup diagram here. Let's say this is low voltage, this is high voltage. I'm just, for an example purpose, I'm just taking a transformer of ratings 100 volts by 200 volts and 50 hertz, 1 kVA, single phase transformer. So let's say you are given with, you have been to a lab, and there you are given with this particular transformer. It's 100 volts by 200 volts, 50 hertz transformer, single phase and 1 kVA rating. Now looking at this, you can tell what is the low voltage and what is high voltage side. So LV side will be 100 volt side and high voltage side will be 200 volts. So yeah. Now what we discussed, when we are going to open circuit test, we have to open this high voltage side and you conduct the test on the low voltage side. Right. Now I'm conducting test means I am placing my instruments on the low voltage side because I want to measure the voltage, current and power readings on the low voltage side. Ammeter, here goes my current coil and pressure coil of a ammeter, wattmeter, sorry, and voltmeter in parallel to measure the voltage this side. And this is my secondary side. I am just open circuiting the secondary side. Okay. Now here at this input we have to give the supply, right? I am giving the full V1, that is rated primary voltage at rated frequency. Now I am giving a rated voltage V1. So how much is the rated voltage in the primary side? That is LV side, 100 volts. Now when I give a 100 volts for a transformer, you will get the 200 volts at the output side. Yeah. So yes, I am just drawing the equivalent circuit for this kind of arrangement. Now I have open circuit at the HV side. HV side, what usually we do, we will connect a load, right? Now since it is open circuited, there won't be any load there. Current won't flow. I will try to draw the equivalent circuit. We remember from the equivalent circuit, just we draw few minutes before. Since it is low voltage side, right? So we have to refer all the parameters to the low voltage side. So that's what we are trying to do. We have provided the transformer with a rated voltage V1, that is 100 volts. I'm just writing it here, V1, RCL1, and this is XM1. Now some current will flow here, that is I0. Now this is open circuited, this is RE1, XE1. So can someone tell me what is the current that flows in this particular branch? I have open circuited it. How much current flows in this branch? No current flows in the secondary branch because we have open circuit at the other side. We are not connecting any load. We just open the terminal, so there no current flows through. Now, what we have understood from this, that is, in an open circuit test, whenever we open the high voltage side and we are given the supply of the rated voltage in the low voltage side, the only current that is generated will be I0, which is nothing but the current required to the passing through the core loss component as well as the magnetizing branch. So we call this current I0 as a no load current. Since there is no load, the only current required is that will be passing through this RCL and XM. So here I0 is the I0 no load current. Now here is my wattmeter. Yeah. Not. This current is I0 and this voltage is nothing but V1. We are assuming all the ammeter and wattmeters are ideal, so there are no losses in the meters itself. Yeah. Let's see. So let's write some equations. Now, for this, if you see the wattmeter, we are applying a voltage of V1 to the pressure coil and the current of I0 is flowing through the current coil of the wattmeter. So what will be the wattmeter reading? That is VI cos phi, where V is applied voltage, V1 rated voltage, current is I0 cos phi. Now the angle will be, that is the angle between voltage and current, that is cos theta naught. We will see theta naught, how we got the theta naught. Now let's say this is V1, that is reference, and if you see the branches, the current is flowing only through this I0 is the only current, and if you see we have an inductance, that is magnetizing inductance, and a resistance. So the drop across this magnetizing branch, let's say this is the current, that is 90 degrees lagging because it's an inductor, and if you see this is the current through core loss resistance, that is ICL, because that is the resistance that will be in phase with the applied voltage. Now the resultant will be the total current, which is I naught. So the angle between V1 and I naught, input voltage and the current, will be theta naught, and the same current will be theta naught here. So that is the no load power factor angle, that is the no load theta naught here. Yeah. Now from the phasor, if you see from the phasor, what we can write, Im is equals to Im1 is equals to I naught sin theta naught, ICL, that is core loss, is equals to I naught cos theta naught. Yeah, these two equations we just got from the phasor, but let's see what we will get from the wattmeter reading. Now from this, I need to calculate theta naught, right? Because all the rest of the values we know. What is the wattmeter reading? We know. What is the voltage, voltmeter reading, and I naught we know. But we need to calculate the theta naught. So how we can get the theta naught? Cos theta naught is equals to wattmeter reading divided by I naught. So now from here I got the theta naught. Now what else parameters we have? Here RCL and XM. Now RCL1 is equals to, if you see the RCL, what is the current flowing through RCL, and ICL1, and this will be IM1. RCL is V1 by ICL1, and XM1 is equals to V1 by IM1. So how to get this ICL and IM? These from here, because you know I naught, you know the theta naught, and you will get IM and ICL. You substitute here and you will get RCL and XCL. So we have conducted open circuit test on a transformer where we have open circuited the high voltage side, and we have placed all our measurement instruments on the LV side, that is ammeter, wattmeter and voltmeter, and we have given rated voltage here, so that the rated voltage is applied, and we will see some current will flow, that is only the no load current. Here we say that no load current is, we can assume, we can say that this no load current will be around 2 to 5% of the rated current. So here we can see how much is the rated current. Can someone tell me how much is rated current? I'm just writing here. I rated LV side. That is kVA rating divided by 100. That is 10 amps. So yeah, our no load current will be around 2 to 5% of this particular 10 amps. So yeah, the only very small amount of current will flow through the magnetizing branch and as well as the core loss component. So that is the I naught value. So now coming to the question, why we are conducting this open circuit on LV side, why we are open circuiting the HV side, not why we are not open circuiting the LV side. So when you see here, when we are open circuiting one end, we have to supply the rated voltage at the other end, right? Now if you see here, now I am supplying the rated voltage of 100 volts in the primary side, I will get the 200 volts at the secondary. Now if you open circuit the LV side and you are supplying HV, what is the rated voltage at HV? You have to supply 200 volts. the meter ratings and the rated currents and the input we have to give will be more. So that's why we are doing this open circuit on the LV side, so that our ratings of the voltage ratings required to give the supply will be less. And we will see the same thing for the short circuit also, and we will have even more better comparison for that. Yeah. So one more thing we have to see here is there is no current flowing through the resistances and here this branch. Usually when a current flows through the primary and secondary resistances and reactances, we will have this I square R losses, that is copper losses. So here there is no copper loss since there is no current flowing through the resistances. Now the only current flowing through will be no load current. So practically what our wattmeter here will read is core losses only, because the only current flowing through the circuit will be required to supply the core loss in the transformer. So practically our wattmeter W0 here you can see that will record only the core losses, and if you see the magnitude of copper losses, how much it will be? It will be very less. That's why we are practically neglect the copper losses in the short open circuit test, and we will take whatever reading that wattmeter is giving us as the core losses. Why it is core loss? Because you see this branch here, this is the core loss branch, and the current flowing through is the only current that is in the open circuit test, and that is being read by our wattmeter. Yeah. Now one more small concept that is in this open circuit test is voltage we are applying is rated voltage. Now when we are supplying a rated voltage, in the last week's discussion we have seen the relation between phi max and voltage. So usually phi max is proportional to V by F. So since the frequency is constant here, you are supplying rated voltage, you are establishing a maximum flux inside the transformer. Now this we know that core we also discussed this hysteresis loss and eddy current losses. These are directly proportional to this phi max. We know that phi max, hysteresis loss and eddy current loss. So we are having a considerable amount of core loss when we are doing a open circuit test, and we are not having this copper losses. Yeah, and we are not having considerable amount of copper losses here. So we are applying a rated voltage, and this is resulting setting up of rated flux inside the circuit, and yeah, so we can the core loss component is very negligible. We are neglecting that. So what we can say, from the open circuit test, we can able to calculate RC1 and XM1. Open circuit test. Our no load current is only 2 to 5% of rated current, as we just discussed. So when that small amount of current flows through the resistances, the I square R loss is very negligible. So that we can write here. Core loss is I square R loss, that is copper loss in open circuit test. Yeah. Now let's flip the same discussion for a short circuit test. One second, someone has joined. short circuit test. SC test is short for short circuit test. Now, the same thing, the way we approach in the open circuit test, we will approach the same. First, we will draw the circuit diagram, like how it will look like. So, one more thing is, short circuit test, we will conduct it on the HV side. That means, we will short circuit the LV side and we will place our instruments on the HV side. And for this also there is a reason, and you will understand why we are doing it like that once we proceed with the discussion. So let me just draw the transformer first. This is LV side and this is HV side. Again my transformer is, example transformer I took, 200 volts, 1 kVA, 50 hertz, single phase transformer. Yeah. So HV side I am placing voltmeter. Here comes my wattmeter. Yeah. Since it's a short circuit, I am directly shorting my LV side. So here the most important thing in a short circuit is, if you remember in open circuit, we have open circuited the high voltage and we have given rated voltage supply to the LV side. Now we have short circuited the LV side. We need to energize our high voltage side. But can you tell me how much voltage we have to give in for the HV side? Can we give the rated high voltage, rated voltage, that is 200 volts to the HV side to conduct the test? The answer is a big no. We should not give the rated voltage, that is 200 volts, to the HV side while conducting the short circuit. Can anyone tell me the reason why we shouldn't give 200 volts? I will just now if you see here, the rated currents in both HV side and LV side are 5 amps and 10 amps respectively. Now since we are giving a supply to the HV, let's say there is no short circuit on the LV side, we have given a high voltage rated, that is 200 volts on the HV side, 100 volts will appear on the LV side, and if it is rated, the rated current which appear on the LV side will be 10 amps. That's fine. But now we are shorting the LV side. It means literally there is no resistance on the LV side, it is zero resistance. Now when you give a rated high voltage here, if you give 200 volts to the HV side, you will get 100 volts on the LV side. Now what will be the low voltage current then? Zero resistance. The voltage is 100 divided by zero resistance. You are allowing very high current to flow in the LV side when you give a rated voltage at the HV side. So that's why you cannot give rated voltage in a short circuit test, because it will lead to a high amount of current flowing in the LV side, because it's a short circuit. So that's the important thing you have to keep in mind while you are conducting the short circuit test. But how we will proceed, how much voltage we have to give, that the problem can be solved by using a auto transformer. Now I am connecting an auto transformer. This is 200 volts, 50 Hz. This is my rated voltage, but I am not giving 200 volts to the HV side, because if I give 200 volts, the amount of current that will generate in the LV side will be very high. So my coil would burn, my transformer would burn. So I won't give that. So what I will do, I will start my auto transformer from the 0 position, 0 volts initially. I will slowly turn that auto transformer. I will slowly increase the voltage of my HV side, so that the current in my HV side won't cross 5 amps. So because I know what is my rated HV side current, that is 5 amps. So I will turn my auto transformer in such a way, slowly from 0 volts. I will turn till the point I reach a 5 amps in the HV side current, because that's my rated HV. I can't go beyond 5 amps. Practically we can go like 5%, 10% above the rated current, but we are just going till our rated 5 amps. So till my ammeter here reach 5 amps, I will turn my auto transformer. Now let's say that voltage is VSC. Now I know rated voltage is equals to 200 volts, but I have applied only VSC, that is very less than rated. This is very important, you have to keep in mind. My short circuit voltage is very less compared to rated. I am not giving rated voltage. So I have given some short circuit voltage. My rated current is generated, that is 5 amps in a HV side. Now the secondary side, I will have a corresponding rated current. What it is short circuited, I will have 10 amps rated current. It's fine, because my transformer is well within my limits. I'm happy with the currents and the voltage values. See, now in this case, ISC, this is ISC and this is VSC, and my wattmeter will read WSC. Now this ISC is nothing but my high voltage rated current. In this case it is 5 amps, and VSC, I don't know, some voltage which is very less than 200 volts, that helps me to generate the ISC. And can someone tell me what my WSC reads? It is nothing but ISC square, I square R, right? RE2. That is the resistive component in the my equivalent circuit of the transformer, and from this we will calculate RE2. Now from this equation I have got RE2. We have, I will just write RE2 comma XE2. These are the equivalent circuit parameters, right? RC and XM we already got in open circuit, so we are left with RE2 and XE2. So from this equation we got RE2 here, and now we are left with XE2. For that, what I will calculate first, my total impedance seen by the supply, ZSC. It is nothing but VSC divided by ISC. Now I got these two are my voltmeter and ammeter readings. I got the ZSC. Now my XE2 will be ZSC square minus RE2 square. Right. So now I have got my XE2 as well as RE2. So see here, from the short circuit test we have got the RE2 and XE2, and from the open circuit test we have got the RC, core loss resistance, and XM, magnetizing resistance. Now all the four equal circuit parameters we are able to get, but the important point which we have to note down is open circuit test is giving us core losses, short circuit is giving us copper losses. Why this short circuit is not giving us core loss components? That we will see here. See, I just did a quick comparison. Open circuit, short circuit. In open circuit test, if you remember, I applied rated voltage to the LV side. V rated. And what is my current in that case? That is no load current. 2 to 5% of I rated. Very less current in my open circuit. Now in the short circuit test, my V is VSC, which is very less than rated. We just discussed clearly why it should not be V rated. Now what is my current? It is I rated. We turned our supply till a rated current flows in the circuit. This is my rated current. I am flowing 5 amps in my HV side, 10 amps in my LV side. So I am getting maximum current out of my transformer. Now see, core losses are proportional to voltage and copper losses are proportional to current. Because we know voltage, why it is proportional to voltage, because it's proportional to phi is proportional to V max. We know we already see hysteresis and SD current losses in the last week. It is proportional to square of V max and it is proportional to 1.6 times the flux. 1 second. Yeah. Now this is the case. And copper loss is proportional to I square R. So the more my current, the more my copper losses. So if you see this open circuit test, I naught is very less. So practically negligible core losses. I am having rated voltage. My voltage is very high. So I will get a proportional core losses. That's why my open circuit test gives me core losses. If you see in short circuit, my voltage is very less than the rated voltage. Now since my voltage is very less, I don't get considerable of core losses. Negligible core losses we will get, and rated current we are allowing it to flow. I have enough amount of copper losses, I square R. So copper losses. And what are the equivalent circuit parameters for this core loss? RC and XM. And what are the parameters for this? RE2 and XE2. So I hope you have understood now what is an equivalent circuit of a transformer, how a equivalent circuit of transformer will look like when we refer it to primary and secondary. From that we have got 4 equivalent circuit parameters, RCXM and resistance and impedances. And in order to find that equivalent circuit parameters in a laboratory using some tests, conducting some tests, what is test we can conduct? This open circuit test and that is short circuit test, and how which test will give us which parameters and what that parameter signifies. So now we have all the theory with us, and we know now if you are given with any kind of short circuit or open circuit results, I am sure you will easily find the equivalent circuit parameters, right? With this theory, let's move forward and solve some questions on the equivalent circuit parameters. So this is my first question. I am provided with a 100 kVA transformer. So now I request all of you to solve this problem along with me. Just keep a pen and paper along with you and also calculator, and let's solve this question along with me so that we will match our answers. So it's all calculations now. We have all the concepts with us, we have all the theory, and let's do this problem. And what is my rating? 2200 volts, that is high voltage side. It is clearly high voltage side. 440 volts, it's a low voltage side. Now, yeah, so this is my rating, and we are provided with OC test and SC test results. Simple. Now, we are asked to find all the equivalent circuit parameters. So what is the first question here? RE1. Yeah, so RE1 is nothing but my resistance that is responsible for my copper loss, right? Whenever you want to find an equivalent circuit parameter related to copper loss, you have to conduct the short circuit test. We just saw that. Now, see, I am interested in short circuit test results to find this RE1. So out of these two, we are interested in this. Now, WSC is equals to 1800 watts, VSC 80 volts, ISC.
Excuse me, sir.
Yes. Yes. Tulsi.
So your voice is breaking.
Okay. Sorry for that. Is it okay now? Okay, I hope now it is all fine. There has been an internet fluctuation here, so I'm really sorry for that. Please let me know if there is any disturbance. ISC. Okay. Yeah, these are all the short circuit values. So RE1. Okay. Now my resistance. Now it's simple. RE1 is nothing but my wattmeter reading is there.
So your voice is breaking a lot.
Okay, I'm sorry for that. I think there is a internet problem is there. A lot of internet fluctuation is there. Okay, let's see if it gets better. Anyway, as we have discussed with the concept, now it's only calculation. Okay, now can someone tell me how much RE1 is? How much is RE1? Can you all hear me?
0.88.
Yeah, right, Tulsi, 0.88. Correct, it's simple. WSC.
Your voice is breaking.
Okay. Internet is not really stable here. I'm sorry for that. Okay. Now we have to find the XE1. So again, it is related to our core loss component, copper loss component only, because that is again I am interested in short circuit test. Now my XE will be how much? In order to find XE, I already know RE1 from the first bit. Now I need to calculate ZSC, then I will calculate XE1. So how much is my ZSC? VSC divided by IS. How much is VSC? 80 by 45. How much is ZSC? Can you type it in the chat box? Please check the answers with me. Please, can someone tell me how much is XE1? Okay. Moving on. Now we are asked core loss resistance. Core loss resistance, we usually conduct open circuit test to find the core loss equivalent circuit parameters. And yeah, I need OC test. 1900, 10 and 440. Here if you see, we were asked to find the equivalent circuit parameters, refer to HV side. Now, since in the first two problems, these two problems are also asked to refer to HV side. Anyhow, since it is a short circuit test, anyhow we conduct short circuit test on the HV side, so we don't need to transform our parameters once we get the answer, because short circuit test is conducted on HV itself. But now we are doing the open circuit test and we are asked to find the parameter referred to HV side. So anyhow we know that open circuit test is conducted on low voltage LV side. Now let's get the answer first in LV side and then we will transform that to HV side. So my R naught LV side will be simple, square of the voltage reading divided by WOC, which is V input, this input V1. How much is this? Now we got the R naught core loss resistances, but it is in LV side because open circuit is conducted on LV side. Now we need R naught in HV side. That is R naught in LV multiplied by turns ratio. Is it this? 2200 by 440. Sorry. How much is it? Yeah. So this is how we have to calculate the core loss. First we calculate the core loss on LV side and we will refer it to HV side. Now the final question is we have to estimate the magnetizing reactance, that is XM. Again, when we are talking about core loss and magnetizing, we have to conduct the open circuit test. Clear? And open circuit test is conducted on LV side. But here the question is to find the XM referred to HV side. So first calculate XM, that is referred to LV side as it is, and then we will refer it to HV side at the final step. Now let's see how we can calculate XM in the first place. So yeah. Yeah. So in open circuit test, we know the no load current. It is nothing but that is following through IC1 plus IM1, right? So if you remember, like this is the no load current. This is zero, no current flows here. Now it is splitted into IC1 and IM1. Now we were asked to find XM. Now we know I0 and IC1. Okay. So we just have to find the IC1 first. Okay. It's nothing but, yeah. First find IM and we can I0 square minus IC1 square. So if you see, IC1 is nothing but the current flowing through the RCL, right? We know the voltage applied and we know the RC1, that is the just the before bit we solved. Now IC1 is equals to 440 divided by 2547.36. Now is the screen visible now? Tulsi, you can type it. Now I got my core loss current that is flowing through RCL, that is this one. From this I will get, thank you, IM1. How much is my I0? 10 amps. Now I got IM. Now how can I find XM? XM1, that is LV side, is equals to, that is the voltage across that branch divided by IM1 LV. 440 divided by 9.99. (44 amps). Now what was asked? We have to XM1 HV side. Now it will be 44 multiplied by turns ratio, 2200 divided by square. How much is it? Into 200 square divided by 440 square. Okay. Around something you will get 0.16 ohm. So now we have got RC1 and XM1 refer to HV side, and XE2 and RE2 refer to HV side. So That's all. So now we have talked about the equivalent circuit parameters of a transformer, how the equivalent circuit will look like when we refer the same equivalent circuit to primary side as well as secondary side. Once we do that, we have discussed different tests, open circuit and short circuit test, to find these particular equivalent circuit parameters, and we saw which test will give which parameters, and then we solve this problem where we are given with our results of short circuit test and open circuit test, and from that we have calculated all these parameters. So yeah, you just have to keep in mind how much voltage we are applying in a short circuit test, how much voltage I am applying in a open circuit test, and how much current is flowing through both the windings. So you don't want to damage your transformer, right? So you don't want to damage your transformer. So make sure you are having all the voltage and currents within the limits. And remember one thing, in the open circuit test you will give rated voltage so that 2 to 5% of no load current will flow. In the short circuit test you will apply voltage such that the rated current will flow. So these are the only two key points in both the tests, and subsequently you will conduct the test and you will get the readings of the wattmeters, voltmeter and ammeter, and from that you will calculate the equivalent circuit parameters. Now there are few more concepts apart from this short circuit test and open circuit test and the equivalent circuit. There are efficiency calculations, loss calculations, and even more analysis on the transformer part. So that you will be having another session by 7 p.m. today, and please join that session, and you will be having few more concepts for discussion there, and that will help you in solving the assignments. So I hope today's session was informative, and I hope you have understood today's discussion. And yeah, if you have any kinds of doubts, or even if you have any kinds of doubts apart from the discussion today, please mail to us. Please raise your questions in the discussion forum. Our TAs will try to address those questions, and you can also note your questions in the class sections, and you can ask those questions in these live sessions every week. So yeah, please do attend all the 3 interactive sessions by our TAs, and you will be covering different concepts. We won't be overlapping anything, we won't be repeating anything, so you will able to cover more topics in the discussions, and this will ultimately help you in solving the assignment problems. So I'm really sorry for the internet problem today. There has been a very fluctuating internet at my side, and let's hope from next session it won't happen. Okay, so with that I conclude today's discussion, and we will meet in the next week same time, Saturday 4 to 5, with more concepts for the discussion. I thank you everyone for your time, and have a nice weekend.